Hello and welcome back. Today I'm going to talk about coordinate systems in geodesy. Let's see how a coordinate system is defined. Normally in mathematics, we see a coordinate system like this shape that I'm showing here. We define an origin for the coordinate system and we define the directions of the three axes of the coordinate system. In geodesy, we can select different points and put the origin of the coordinate system on that. For example, when the Earth's center or center of gravity, the Earth, is selected as the origin for the coordinate system, the system is called geocentric. If we consider the Sun center as the center of the coordinate system, the system is called heliocentric. Heliocentric means that the center is the center of the Sun. Selenocentric, when the center of the Moon is the center of the coordinate system. And topocentric means that the Earth's surface or any point at the surface of the Earth is the origin of the coordinate system. So then the direction of the z-axis. It can also be defined in different ways. It can be the Earth's rotation axis, normal to ecliptic plane. Ecliptic plane is a plane at which the Earth orbits around the Sun, or normal to orbital plane for example satellite geodesy. When the satellite is moving around the Earth, it creates an orbit, and we can consider the normal to that orbital plane as the z direction, or we can consider tangent to plumb line or normal to the ellipsoid. When we look at the Earth with mathematical eyes, it means that we see the Earth as an ellipsoid. This x-axis is more conventional because the Earth is rotational, and we can select any meridian actually and consider it as reference. In our time for the terrestrial coordinate systems, we use Greenwich meridian. Greenwich is the name of an observatory close to London. And also for the celestial coordinate systems that we apply in geodesy, we can consider vernal equinoxes, which is the point which is constant in the space. We can consider that one too. And the last point, or the direction of the y-axis, is defined based on the type of the system. If the system is left-handed or right-handed. What does it mean when I say right-handed? Right-hand system, if I have this thumb along the z-axis of the system and the index finger towards the x-axis of the system, and I can complete a coordinate system by the middle finger like that with my right hand, then the system is called right-handed. And if I can complete the coordinate system by my left hand fingers, then I have a left hand coordinate system. As I explained, after defining the origin of the coordinate system, we have to define the direction of the z-axis. In terrestrial coordinate system, the z-axis actually is the Earth's rotation axis. So it means that the z-axis is pointing towards north. But the point is that the pole position or the north is not steady. It's changing in time because of the Earth's mass inhomogeneities. What does it mean? It means that some places of the Earth are heavier than the other parts, or the opposite, some places are lighter than the rest. This causes that when the Earth rotates, extra movements are observed or irregularities happen in polar mode, the pole position. This movement has a period of about 1.2 years or 430 days period with an amplitude of about 5 meters. For example, this plot, which is showing the polar motion or the position of the pole from January 1969 up to December 1969, and determined by two organizations, BIH in Paris and International Polar Motion Service. And as you see, the amplitude of this movement is around 5 meters. Then if the z-axis of the system is changing, then how should we define a fixed coordinate? It was the International Union of Geophysics and Geodesy decided to define an average, which is called conventional international origin, and they measured the pole position during these 5 years from 1900 and 1905 based on the observation of latitude of 5 observatories and took the average. And they considered that point, that average, as the pole position and defined the average coordinate system based on the CIO or the average pole position. Instantaneous and conventional terrestrial coordinate systems. As you have noticed, we define CIO, and based on the CIO, we define a conventional terrestrial coordinate system, which simply I show this here by CT. CT means conventional terrestrial. In some literature, you may see CTS or CTF. They are the same, but they are actually defined based on the CIO, the average pole position. And also we can have instantaneous terrestrial coordinate system, which is changing all the time. So if we have the average for defining the coordinate, the true pole, which is instantaneous, has another position, which is different than CIO. If CIO is here, the instantaneous pole is here. And this is very important, especially for satellite geodesy, when we have to consider all small movements of the coordinates. So in that case, if we have CIO, which is fixed, we can determine the position of the true pole based on the CIO. For example, we see this side is actually parallel along this y-axis of the system. Then it will be y coordinate of the pole or instantaneous pole, and this will be is along x, and this is the x coordinate of the instantaneous pole. So theoretically, we can show these two movements by two rotation. One rotation from here and one rotation from here to fix or to transfer or transform the coordinates from CIO, the average coordinate system, to the instantaneous coordinate system. Astronomical and geodetic coordinates. We have already discussed this point. Consider the geoid on the left-hand side and the CT system, or the conventional terrestrial coordinate system, in it. And also on the right-hand side, we have the reference ellipsoid or biaxial ellipsoid and geodetic coordinate. And we assume that the center of both points are most center of both coordinate systems coincides. So, as we observe, we can define a Greenwich astronomical meridian for the true Earth, the physical Earth, and we can define Greenwich geodetic meridian for the mathematical Earth. We can define plumb line for at any point at the Earth's surface, and we can draw a tangent line to plumb line to that. Similarly, we can do the same for the mathematical Earth, but this time instead of plumb line, we will have the normal to the ellipsoid. And we can define the local astronomical meridian, which can contain this tangent to plumb line. And here we can have local geodetic meridian containing the normal to the ellipsoid. And we call this height topometric height, if you remember, and this height geodetic height. Lambda is the astronomical longitude, the angle between the Greenwich astronomical meridian and local astronomical meridian. Similarly, we can define geodetic longitude between the Greenwich geodetic and local meridians. Similarly, we can define astronomical latitude and geodetic longitude, as you see here. But the point was not to define these parameters. My point here is to define the local coordinate systems. For example, if we have a point I at the surface of the Earth, and I draw an axis along the tangent to plumb line, I can call this axis z-axis of the system, and I say R means local astronomical. I can do the similar thing, but this time along the normal to the ellipsoid, and I call this z-axis of the LG system. L means local and G is geodetic. So I'm talking about local astronomical coordinate system and local geodetic coordinate system here. Axis of the system here is pointing toward north. And here, x-axis of the system is also pointing toward north. But consider that this is a mathematical Earth, and this one is physical Earth, and the pole may not be the same or at the same position. We can call it geodetic pole or north of ellipsoid, but this is rather true north. And the system is like that in both. Means that if I put the thumb along z-axis and index finger along the x-axis of both the systems, I observe that only with left hand I can complete the system. It means that the system is left-handed. So I have defined two local coordinate systems here. Local geodetic coordinate system when the Earth is mathematical, for the mathematical Earth, and for the real Earth or the physical Earth, I can have local geodetic coordinate system. One is defined based on plumb line, one is defined based on the normal to the ellipsoid. Both x-axis are pointing towards north, but north of the true north for the physical Earth, and geodetic north, or the north of ellipsoid for the mathematical Earth, and both systems are left-handed. Here I give you a summary for terrestrial coordinate system. Coordinate systems are global or local. If they are global, they are geocentric. If they are local, they are topocentric. The global ones, the z-axis, are along the Earth's rotation axis, and the rotation axis can be instantaneous or average. If it is instantaneous, then the meridians and equators and coordinates will be instantaneous. And if it is average, the coordinates will be average. Meridians and equators are average. But z-axis for the local system are the space. If you are on the physical Earth, is the tangent to the plumb line. Or if the Earth is mathematical, then no more to the ellipse. The axis is defined for terrestrial systems towards Greenwich meridian. And again, if the z-axis is instantaneous, the Greenwich meridian will be instantaneous because this meridian is defined based on the z-axis. And if it is average, then it is the x-axis or the Greenwich meridian will be average. For x coordinate for the local, it's towards north. Again, if the north is true north or astronomical north, then it is or average or astronomical or pole. Or if you have mathematical earth, then it will be geodetic pole or ellipsoid. And all global coordinate systems are right-handed and local ones are left-handed. So I have made them in red, and you can observe this is very common for all global coordinate systems. They are all geocentric. Local ones are topocentric. All of them are the global one right-handed and the local one left-handed. That's a general standard for in geodesy. The National Terrestrial Reference System, which is nothing else than the CT system that we have already defined, but a little bit more precise and practical. For example, the origin of the Earth center is defined as the center of the mass. It is somehow geocentric, but it is considered also the atmospheric and ocean masses. And atmosphere and oceans are changing all the time. Then the position of geocentric can change as well. And the z-axis is towards CIO again, but this CIO is the update, not the old CIO, which is between 90s, not up to 1905. It is the new definition by BIH in 1984. But the principle is the same. Again, x-axis of the system is the Greenwich meridian, and it is based on the z-axis, which is going through this CIO 1984. And as I explained, the international terrestrial, this is somehow a global system, then it is right-handed. For defining the distances or the length or scale in the system, they use speed of light for definition of this distance or length. And also to define, to have the frame stable, they consider no net rotation condition, which balances how the motion so that some plates may move east and some others to west. But in overall, the system as whole stays still, no global rotation. Let me explain this a little bit more. If I have, for example, I have a car here, another car here, another car here, one moving northward, one moving eastward, and one moving westward. If I define one of these, I consider one of these cars as a reference and consider coordinate system origin on this car. When this car moves, all positions, all the coordinates of the other things or the cars will move as well. So we should define a coordinate system which are not actually dependent on the movement of these points of the car. It is exactly the thing that we do for the principle of the no net rotation. So these cars are similar to the points at the Earth's cross, which are moving actually. But we want the coordinate system not to be dependent on these movements. And this is why we say no net rotation. We consider the system in such a way that if the points are moving to some places and the other points are the average of the changes of the coordinates are zero. This means that the coordinate system is not affected by the movements of the points on the Earth's cross. The National Terrestrial Reference Frame, a practical realization of ITRS. It has three translations, which in fact define the origin, three rotations for the orientation of the system, and one scale, plus the temporal changes of the coordinates and rotations and translations. Therefore, we have 14 parameters to estimate. And the SLR data, VLBI data, GPS, DORIS, and LR data all are used for defining coordinates of defining this coordinate system. And the very early version of this ITRF system relied heavily on SLR or satellite laser ranging observation from CSR, Center for Space Research, Texas. And based on the epoch that we have, reference epoch for ITRF that we have, and the time that has passed from that, and the velocity of the coordinates, and the initial coordinates, plus some corrections which are computed based on tide, ocean tide, atmosphere, and other factors. The coordinates of the points in the new time or the current time can be computed